Hello everyone. In this video we are going to talk about the notion of Jacobian. Okay? In the previous video we talked about angular velocity. Why did we talk about it? Because if you look at the end effector, in general it can have 6 degrees of freedom, right? It can, and those degrees of freedom coming from, in general, the rest of the joints of the robot. And those joints can give this end effector its x, y, and z motion, as well as theta x, theta y, and theta z, the absolute angle of the end effector frame with respect to the inertial frame. If we call those absolute angles, theta x, theta y, theta z, okay? So not Euler angles, absolute angles. And then if we have these 6 basically values for end effector, and if you look at the time derivative of these 6 values, the derivatives of x, y, and z will form the linear velocity of the end effector. So as you can see here also, the linear velocity of the end effector, Vn with respect to the base, is what? Is the position vector of it, O, which is, you take a time derivative, so it's O dot or D dot. And also, the angular velocity of the end effector with respect to base is defined as R dot R transpose. The skew symmetric matrix of that is defined as R dot R transpose. So if you go here and go and look back, you see that the skew symmetric of omega of end effector with respect to I written in I. Here we, instead of E and I, we call them N and 0, but that's the same thing, is R dot R transpose, correct? So here this equation describes, based on the rotation matrix of the end effector with respect to base, this describes the angular velocity of the end effector, and then the derivative of the origin of the nth frame with respect to the base frame, the time derivative of that, which is time derivative of x, y, and z, that will define what? The linear velocity of the end effector. So now, this is the goal here. This is the goal. The goal is this. Can I write the linear velocity of the end effector as some matrix multiplied by the vector of joint variables? And can I also write the angular velocity of the end effector also as another matrix times the vector of joint variables? So this q dot here is a vector, okay? When you say here q dot, this q dot that you see here is a vector. What is that? This vector q dot is the vector of all joint variables. So let's say if your robot has 6 joints and you call these joint variables q1 to q6, where q could be a theta or a d, right? So theta 1 is the same as q1, theta 2 is q2, d3 is q3, and so on. So instead of calling them theta and d, if you just call all of them q, and let's say, for example, you have 4 or 6 or whatever joints, then something like this, q1 dot, q2 dot, q3 dot, and so on all the way to qn dot, where qn dot is the last joint time derivative, okay? This is that vector q dot. For example, for a Scara, it's going to be theta 1 dot, theta 2 dot, d3 dot, theta 4 dot, right? And so on and so forth. So this is the vector of the joint velocities, right? This is the vector of joint velocities. Then, if I can write the linear and the angular velocity of the end effector as some matrix multiplied by this, I can combine these two velocities, linear and angular, into one single vector, call it zeta, as you can see, where the first 3 components of it are v, the next 3 components of it are omega. So you know v is a 3 by 1, it has x dot, y dot, z dot. Omega is theta x dot, theta y dot, and theta z dot. So You stack this 3 by 1 and 3 by 1 on the top of each other, you get a vector of 6 by 1. What is this vector zeta? It has all of the velocities of the end effector, the 3 linear ones and the 3 angular ones, this zeta. And if you can combine those two matrices, JV and what? J omega, if you can combine them together, then you can form a matrix here and call the whole matrix J. So what you can do is you can write those two relations as one single relation and say that J, the vector of end effector velocities, is equal to what? Is equal to this matrix J times the vector of joint velocities, right? So let me again write it for you. This is the vector of, these are the end effector velocities, and I mean all of it, linear and angular. And this q dot here is what? These are the joint velocities, theta 1 dot, theta 2 dot, and so on and so forth. If I can relate these guys together by a simple matrix product, in other words, by a linear relationship, this relation, first of all, this equation is what we call differential forward kinematics. So this is differential forward kinematics equations. Okay, these are called differential forward kinematics equations. And this matrix that relates these two important joint vectors together and the end effector speeds together, velocities together, this matrix J is what we call the Jacobian of the end effector. Okay, so here we learn about some terminologies, correct? Now, the importance of this is this relation is way simpler than the forward kinematics equations, because in forward kinematics equations, for example, if I have a what? I have, let's say, the 2 degree of freedom planar R, okay? Here, the end effector only has really x and y. So you have some, if end effector moves like this, you have some x of the end effector dot and some y of the end effector dot. These are the components of the velocity of the end effector in base. And these angles, as you know, this is theta 1, correct? And this is theta 2. And so if you remember, and also here we can call them x of end effector and y of end effector. When we wanted to go from the joint space, which is theta 1 and theta 2, to what? To the workspace, which is xe and ye. The relations, if you remember, they were not here maybe I call it n instead of end effector, or because I'm mixing here. So it's better to call it end effector in I, because we either go e and I or go n and 0, right? So it's better to stay consistent. So here we go. These guys, if you remember, I could not write them as some matrix 2 by 2 times what? Times theta 1 and theta 2, which are my joint variables. So if this was my vector q and this was my end effector position, whatever you want to call it, I could not write them as a linear combination of these, right? Because, for example, if I call this guy J11, J12, J21, and J22, you clearly see this leads to two linear relation that x of end effector in inertial is some number times theta 1 plus another number times theta 2. You know it wasn't the case, correct? There was no linear relation like this. If you remember, your forward kinematics equations were what? Were all nonlinear. So I could never write them in a matrix format. You can only do when everything is a linear relation. And they were not. So I could never do such a thing. If you remember, your x was basically, if you call these A1 and A2, the length of the members, it was A1 what? Cosine of theta 1, and then plus A2 times cosine of theta 1 plus theta 2. And you had a similar thing for y. So there was no way you could write these relations as something linear. Even if you called sine and cosine of thetas some other variable, still you could not do it, okay? Because here those sines and cosines are multiplied together. So these relations were absolutely nonlinear, and there was no way to reduce it to linear. There was no way. But now, instead, I'm saying, well, I cannot do that, but what I can do is to write the derivative, time derivative relations, which is what? Which is x e in I dot and y e in I dot. Can I write those as a linear relation? So write those as some 2 by 2 matrix. And then what? The joint variables, but the velocity of them. So here theta 1 dot and theta 2 dot. Can I write the derivatives based on each other as a linear relation? The answer is yes, you can, and I'll show you. Okay, and then this matrix is what relates them together. It is very important matrix. It tells us a lot about the manipulator. We'll see. It tells us about singularities. It tells us about how it converts the joint motion into end effector motion, or the forces and torques to each other. And it tells us other stuff we call manipulability. We're going to see that. So this is a fundamental important matrix. Now, does it mean these components are just constant number? The answer is no. These guys are going to be functions of the joint variables. Each one of these components are not going to be constant. But they are not going to be functions of the velocities. They are going to be functions of what? The thetas, the variables, not their time derivatives. Okay, so this J matrix is not going to be a constant matrix. You'll see in general, this is a function of what in general? Each component in it can be a function of theta 1 and theta 2. So from one point to the next, when the robot moves, the value of this J does change. Okay, so that's the whole idea of the Jacobian, going from joint speeds and velocities to end effector velocities. Good? Now, there are several ways to calculate this very important matrix. One of them is using partial derivatives, which I'll show you. And the other one is if you use the DH convention. I also show you how you get the J matrix through the DH convention. And then as we go through the future lectures, I'll show you the importance of this J matrix, okay? As we go from one topic to the next, from inverse velocity problem to differential inverse kinematics to static force analysis to you just name it. This one is not a super application. What is this for? Singularities, then manipulability. In each one of these, you see the J matrix is there. Okay, so each application and important topic that we talk about the robot, the J is there. Okay, other than forward and by inverse kinematics, everything else, J would show up itself. Okay, So that's such a hugely important matrix. Now, if I show you, let's go back to this example we were working on. So the question is, in this case, how can I write my x and y dot in terms of theta 1 dot and theta 2 dot as this matrix format? So take a look here. All I need to do is to basically take time derivative. That's all it is. Take time derivative from these equations, see what you get. You will get x of e in I dot is equal to what? What is time derivative of a1 cosine of theta 1? Well, it is negative a1 sine of theta 1. But since you are taking time derivative, not derivative with respect to theta 1, there will be an extra term, which is what? Theta 1 dot, correct? That comes from the chain rule, right? Take a look here. I'm taking the derivative of sine of, or cosine of, in this case. What's the derivative of cosine of theta 1 with respect to time? Okay, and this is, you cannot do it directly. Why? Because this is a function, this guy here, this cosine theta 1, it is a function of theta 1 explicitly, not function of time. If it was derivative of that with respect to theta 1, so like this, directly from calculus, you say, well, that's negative sine of theta 1, right? But here, if you look, the denominators are different. I cannot say these are the same thing unless I multiply this by d of theta 1 with respect to dt. Now, it's kind of like simplifying these two together and getting my original ratio back. Now, the question is, what is this? Well, based on what you know from calculus, that's negative sine of theta 1. And what is this one? That is theta 1 dot. So you see where this extra theta 1 dot or omega 1 comes into play. Okay, that's called chain rule or implicit taking derivatives, right? Implicit differentiation. So this is why, as I said again, those theta dot terms are showing themselves. Good. So let's go back and continue with the rest of the derivatives. So that's the first term. Now what? Take time derivative of this. So there's going to be negative a2 times sine of theta 1 plus theta 2, and then the time derivative of the whole thing that is inside, which is going to be theta 1 dot plus theta 2 dots. And then you can do a similar thing here for y. So it is going to be a1 cosine of theta 1 dot plus a2 cosine of theta 1 plus theta 2 times theta 1 dot plus theta 2 dot. And if you want, you can organize it a little bit better. Just factor out theta 1 dot and theta 2 dot if there is any term. So theta 1 dot times what? What's the coefficient of theta 1 dot? It is negative a1 sine 1. So here I use short notation. Negative a1 sine 1. And then what? If you look, it is negative a2 sine of 1 plus 2. And then plus theta 2 dot. What? Negative a2 sine of theta 1, 2. Similarly here, it is going to be theta 1 dot times a1 cosine 1 plus a2 cosine 1, 2, and then plus theta 2 dot times a2 cosine 1, 2. So I can write it like this. And now with that relation that I wrote, can I write it as this matrix format, this linear relation format? The answer is yes, I can. How? Well, if you look here, let me expand this a bit, give it some room. Good. So let's look at the coefficients here. When I want to write xe dot with respect to x dot with respect to theta 1 and theta 2, the coefficient of theta 1 dot is this. So that comes here. Then the coefficient for theta 2 dot is this guy. So that comes here. The coefficient for theta 1 dot for y dot is this one. So that comes here. And the coefficient for theta 2 dot is this one, which comes here. Done. Okay, so as you can see clearly, this matrix that I got allowed me to write my end-effector velocities in terms of the joint velocities as a linear relation. Second of all, this matrix that I call J, it's not constant. It is a function of what? There is theta 1 and theta 2 in each component. So in general, it is a function of theta 1 or theta 2, or in general, with that Q notation, they say J is a function of what? Vector Q, okay? So it's not constant. It changes from point to point as the robot moves, theta 1 and theta 2 change. But clearly, this relation here, the components here do not depend on the velocities. Okay, so that is your Jacobian. Now, what's the importance of this matrix? I'll tell you. As we go through more and more applications in future slides, I'll show you the importance of this matrix. But for the moment being, the simplest application is this. I have this robot. And now I'm going to rotate my first arm with, let's say, for example, 20 radians per second, counterclockwise. And then I'm going to rotate my second link with the theta dot 2 equal to, let's say, 10 radians per second. And I know the size of each link. So this is like 0.2 meters. And A2 is like 0.15 meters. The question is, what is x dot, what is y dot, or what is what? This vector of the velocity of the end effector in I. Okay, so for a robot with this geometry and with this speed of the joints, how fast the end effector is moving, right? So all I need is to go back here and plug in the numbers, right? Say that, hey, this theta 1 dot is positive 20, the theta 2 dot is negative 10 because it's clockwise. And then I have A1 and A2. The other thing as you see, you need what? Theta 1 and theta 2. So although I have theta 1 and theta 2 dots determined and A1 and A2, the output does depend on how much is your current theta 1 and how much is your current theta 2. If I change my configuration of the robot with the same inputs, velocities of the joint, and with the same geometry, I will get different numbers. So here I'm going to look at separate scenarios. Scenario 1, let's say theta 1 here is, for example, 60 degrees. And theta 2 here is, let's say, 30 degrees, but clearly you see that it is negative, right? Because it is clockwise. So I'm going to plug in all these numbers, and I'll use MATLAB here to help me multiply the numbers, right? So I say my J matrix, and I can use symbolic if I want and use the eval command, or I can use anonymous functions. So for the moment, let's use symbolic functions, right? So sims of, let me write everything in a script if you don't mind. So here we go. So sims of T1 and T2, I use them instead of theta 1 and theta 2. And then I also need T1 dot and T2 dot. And then what? I also need A1 and A2. So my J matrix is this. The first element, as you can see, is negative A1 S1, negative A2 S1, 2, correct? So here, negative A1 S1, negative A2 times S1, 2. Then you simply have negative A2 S1, 2, which is this guy. That's your 2 element. You go to the next row. That is A1 cosine of T1 plus excuse me, A2 cosine theta 2, theta 1 plus 2. And then the last element is this guy here, correct? And if you want, you can use 3 dots and go to the next row. So that is my Jacobian matrix. My joint velocity Q dot is what? It is T1 dot and T2 dot, theta 1 dot and theta 2 dot. What I need to calculate is what? My V of the end effector, which is equal to what? J times Q dot, correct? Right? So here I define everything. Now here I plug in some numbers for them. So I say T1 is 60 degrees, right? Or pi over 6. T2 is negative 30 degrees. But remember here I use sine and cosine, not sine d cosine d. So I need to make sure I write it in radians. T1 dot was, go back here, let's see what numbers we used. So we had 20, 10, 0.2.15. So we had 20, 10, but negative 10 actually. And then 0.2 meters and A2 is 0.15 meters. So I define the numbers, and now you say evaluate my V of the end effector. So basically means plug in all of these numbers into those symbolic formulas and evaluate the number here and give me how much. So if I run this and I call it whatever you want, so I can call it Jacobian 2DOF planar arm demo, right? And I change my folder and get the number here. Then give me an error. Seems like I forgot some asterisk or something somewhere here. Okay. This is the number. It says the speed of the end effector is negative 2i plus 4.96 j, correct? So it says, based on what you said, your end effector at this moment should move something like this. Not everything screwed up, but so it should move negative 2i and what? How much was it? 4.96J, so it should move in this direction. Negative I and positive J. Okay, and the main reason it is moving backwards is this theta 1, which is dominant, 20 instead of 10. Okay, so this is the total resulting velocity of the end effector due to both of these motions at the same time. Okay, so you can change any number that you want. You can change the configuration. That will lead to a change in the end effector velocity. You can change the rotation velocity, the angular velocity of the members. That will also change the number here, right? And you can change the geometry. But let's say the robot is made so the A1 and A2 are fixed. So if I want a specific velocity from the end effector, what can I do? Well, I have to look at what angle basically I am positioned right now, correct? What is my theta 1? What is my theta 2? And then based on that, I figure out how much theta 1 dot and how much theta 2 dot I need to make that velocity happen. And that problem is our topic of the next slide here. Here is called inverse velocity problem, and we get to that, okay? But you clearly see that having your Q dots and your J matrix will lead to end effector velocities. Sometimes you go backwards. Most of the time you actually go backwards. You want a desired end effector velocity. You know the angle you are at the moment. What you really need are those Q dot values, how fast to turn each joint in the robot. And you can find that, again, we call it inverse velocity, and for that you need the inverse of this Jacobian matrix. Okay, so we'll talk about that and about singularities and stuff, but just want you to see the importance of this guy to take your space from joint space to the workspace. Good. So now if we want to calculate this Jacobian matrix in general, that was a very simple robot, 2 degrees of freedom, took time derivative and no big problem. But in general, if you want to define this Jacobian matrix and how to calculate it, as I said, I tell you 2 major ways to calculate this important matrix. One is using partial derivatives, and this is almost the same as what we did right here in this case. So here, let's assume that the x, y, z positions of the end effector in base and the absolute angles, theta x, theta y, theta z of the end effector frame in the base frame are in general functions of what? Functions of the joint variables from q1 to qn, okay? So each one of them is a function of those joint variables. If I take time derivative from both sides of this equation, these guys are going to be x dot, y dot, z dot. These guys are going to be omega x, omega y, and omega z. So this whole thing here is what? This is that zeta vector that you introduced earlier, correct? The vector of end effector velocity, because the first 3 components are v, the next 3 components are omega. So this whole thing here is that zeta is equal to. So here these functions f1, f2 all the way to f6 are functions of what? Functions of q's, but I'm taking time derivative from them. Since they are not function of time explicitly, they are function of q's. The q's are functions of time. So again, here I have to do what? I have to do, yes, you are right, the chain rule. And so instead, I take the derivatives of these functions with respect to their own variables, which here I show with partial derivative of fi with respect to qj. as a matrix and multiplied by q1 dot, q2 dot, q3 dot, all the way to q6 dot. And again, this extra term comes from the application of the chain rule. Okay, so this is clearly your vector q dot that you have up there. So you see that your zeta is some matrix times q dot, so that matrix has to be what? Your J matrix. So clearly the Jacobian is what? The partial derivative of each one of these functions with respect to what? One of the variables. Okay? So let's say if we go back to the case of that 2DOF planar arm, if you see here, this x is a function of the two angles, so I can call this f1 of theta 1 and theta 2, and the next variable of the end effector y is also another function of theta 1 and theta 2. Okay, so when I say partial of fi with respect to qj, what does it mean? In this case means in each row you keep your f constant and you change your variable. So it is like partial of f1 with respect to q1, partial of f2 with respect to, f1 with respect to q2. You go to next row, you change f, and again you take the derivative with respect to all q's. And so on and so forth, right? And that's what you learn in calculus, right? The Jacobian matrix. Partial derivative of multivariable functions with respect to all of those variables, correct? It's called the Jacobian matrix, and that's the exact same thing here. So your q1 and q2 here, you call them what? Theta 1 and theta 2. So if you want, you can get rid of these q's and replace them with what? With theta. So you can call it with respect to theta 1 and theta 2, and here again the same thing, theta 1 and theta 2. And that, as I said, what we call a Jacobian matrix. Now what is it in this case? So what is this first component? Partial of f1 with respect to theta 1. What's the partial of this function with respect to theta 1? Here you don't need to take time derivative, just theta 1 derivative. So when you take derivative with respect to theta 1 means everything else has to be considered or treated as a constant. So in theta 2 you can treat it as a constant. Derivative of this is negative a1 sine theta 1. Derivative of that is what? Negative a2 sine of what? Of course, the derivative of negative a2 sine of this whole thing, theta 1 plus theta 2, which if you look at it, it's exactly this guy. So this one, for that f1, is going to lead to what? To this. Yes? Then what is partial of f1 for theta 2? Well, the first term has no theta 2 in it. The second term is simply negative a2 sine of theta 1 plus 2, which you see is exactly this one. Right? Then what is the partial of f2, which is this function with respect to theta 1? Well, it is going to be a1 cosine theta 1 plus a2 cosine of 1 plus 2, which is exactly this. And finally, if you take derivative of that with respect to theta 2, that is going to be what? a2 cosine theta 1 plus 2, which is exactly this one. So you see, I could get this matrix by taking these partial derivatives of each one of those functions, f1, f2, and so on, with respect to what? Theta 1, theta 2. So in each row, as I said, the function is constant. In each column, the variable is constant, as you can see. And this is called the Jacobian matrix, right? So one way to do what? To do Jacobian is using these partial derivatives. So here we have done this planar 2DOF arm. So maybe we try something different. Let's work about 3 degree of freedom planar arm, right? Let's do something a little bit different. So the 3 degree of freedom planar arm is something like this. And I can call these members A1, A2, and A3, and then I can provide 3 angles. So this one is your theta 1. This one here is your theta 2, and this one here is your theta 3. Okay, and if I use x and y axes here, this point has, and call it the end effector, this point has x of e and y of e, and it also has an angle. If we call this angle here this angle psi, or you might call it theta z, for example. If I want to write that theta z and x and y as a function of the 3 joint variables, what do I have? Your x of end effector in inertial is going to be a1 cosine of 1 plus a2 cosine of 1, 2 plus a3 cosine of 1 plus 2 plus 3, so I can write it like this. Your y of the end effector in inertial is a1 sine 1 plus a2 sine 1, 2 plus a3 sine 1, 2, 3, and finally your theta z angle is simply sum of the 3 angles. Right? That's what you have. Here there is no theta x, no theta y, and there is no z because it's all planar. And you have these 3 things that you can determine for the end effector. So now if I say what is the velocity of the end effector, which is in this case is x dot and y dot and theta dot, which you can call what? Omega z, right? One, you can call it theta dot for now. If I say what are these, so if you want, you can call the first 2 components to be vector v, the linear velocity of the end effector, and this single component, call it what? Omega of the end effector. But you know, omega is only omega z, correct? That's all it is. But you can also call it a vector, but in this case, that's just a scalar. It's not really a vector. So what is this? You can write it as a matrix times the joint variables, their time derivatives, which are theta 1 dot, theta 2 dot, and theta 3 dot. And this guy, as I said, you call it vector q dot. And this guy here, you call it vector zeta. So this connecting matrix, you can call it the J matrix. Now, what is that? Per definition that we mentioned, if you call this whole thing F1, you call this whole thing F2, and if you call this whole thing F3, that matrix is partial of F1 with respect to theta 1, then the same function for theta 2, then the same function for theta 3, then you change your function, you go now to F2, and repeat all of these partial derivatives. and then you go to F3 and again repeat. Right, so once you do that, then you're ready to just calculate those derivatives. So what is J gonna be? So based on those definitions, this J is gonna be what? Take partial of F1 with respect to theta 1. Theta 1 is in all of the terms. So it's gonna be negative A1 sine 1, negative A2 sine 1, 2, negative A3 sine 1, 2, 3. For theta 2, it's only in the second and third term, so it's going to be simply negative A2 sine 1, 2, negative A3 sine 1, 2, 3. And the 3 is only in the last term, so you only get negative A3 sine 1, 2, 3. Then you take partial derivative of the y with respect to the same three variables. For theta 1, again, all three terms are there. So you will get A1 C1 plus A2 C2 C1 2 plus A3 C1 2 3. This is going to be A2 C1 2 plus A3 C1 2 3. This is going to be simply A3 C1 2 3. And partial of the last function, which is sum of them with respect to each one, is simply 1. So this is your Jacobian matrix. So now at any angle, this J, which clearly you can see it is a function of all three joint variables. At any angle, since I know the geometry, which is A1, A2, and A3, if I know the angles, I can determine this whole matrix. If now somebody gives me the joint velocities, I can determine what? The end-effector velocities. Okay, or if somebody give me the end-effector velocities, I can invert this, multiply from left side, and determine what? The required joint velocities, which again we call it the inverse velocity problem. Okay, so taking partial derivative here, we did it for the planar 3D OOF. So the important thing is you have these functions. If you have these functions, then it is not so hard. It's just partial derivative. The question is, where do you get these functions? Where do you get these functions? And the answer is from what? Forward kinematics. These equations are your forward kinematics equations. With one twist, of course. What is the twist? The twist is this. When you calculate the forward kinematics, it gives you something like this homogeneous transformation matrix. It gives you a rotation matrix and it gives you O, the origin of the end effector in base. This O here will give you what? Will give you X, Y, and Z that you were after. So these three things that you wanted, the first three functions, they come directly from the elements what? 1 and 4, 2 and 4, and 3 and 4 of the homogeneous matrix of the end effector. The problem is with the last three. The problem with the last three is this. When you look at the last three, these are the absolute angles of the end effector frame with respect to the base frame, as a function of the joint variables. And the problem is these guys are not explicitly given to me. They are implicit into this what? Into this rotation matrix. And the matter of fact, most of the time this rotation matrix is written in terms of what? In terms of intrinsic rotations, which are rotations with respect to what? You're right, with respect to current frame. These thetas are absolute. They are with respect to the fixed frame. They are with respect to what? They are with respect to the base frame. So these are the angles of one frame with respect to another and absolute angles. Okay, so the question is, how do I get these angles? Right? How do I get these angles? Because if I have basically my first frame is I here, so this is xi, this is yi, this is zi. I do a rotation about, let's say, x and theta x. X of I, of course. It gives me some new frame, okay? Then I'm not going to rotate this new frame about the current y. I'm going to rotate it about the old y, the absolute y. So everything here has to rotate about what? About the absolute y for an angle of theta y. Okay? So this is going to be the rotation about y, I, and theta y. And then what? Whatever that you get now, that is completely distorted like this. Now you are going to, again, rotate it not about the current z of this axis. You're going to rotate it about what? Z of I for an angle theta z. Okay, so you get some, let's say, final frame like this. And this rotation matrix R and 0 describes this, whatever is, for example, let's say this is x of end-effector, this is y, right? You have to keep track of them, but this is actually x of end-effector. This is z of end-effector, and this is y of end-effector. So you have to keep track of that and see with these three angles, theta x, theta y, theta z, about absolute x, y, z. When I give you a rotation matrix of E with respect to I, how do you get those three angles, theta x, y, z, back? And if you remember, for that, you have to do what? You have to do the inverse problem. So your rotation matrix R of n0 here, or E in I, that I give it to you as a function, this has to be what? It has to be rotation x, y, z, theta x, theta y, theta z. And if you remember, when I do several of these after each other, I have to multiply the rotation matrices. But since they are extrinsic, the order is reversed. So instead of first multiplying r of x and theta x, I'd first do r of z and theta z, multiplied by r of y and theta y, multiplied by r of x and theta x. Okay, so that is going to be a big jumble of theta x, theta y, and theta z functions. You set it equivalent to this rotation matrix that you have, and each one of them is just a function of something, correct? Right? And then each one of these, as you can see, is going to be a function of these three angles, theta x, theta y, theta z. And then you have to do inverse orientation problem and then find these three angles based on the entries in that matrix. And now that hopefully will give you these functions that you need. So that's the problem we have is this. The orientation of the end effector in base is rarely determined or defined by its absolute angles. That's the problem. Okay, that's the orientation of the end effector in base is rarely defined in terms of its absolute angles. Most of the time it is described in terms of what? It's what we call intrinsic rotations, like what? Like Euler angles, for example. In that case, finding these three equations is a little bit harder. Okay, and for that, we need to discuss something called analytic Jacobian. So this Jacobian that we are discussing here, the name of it is called, this Jacobian that we discuss here, the name of it is called geometric Jacobian. And it works with the derivatives of x, y, z and absolute angles theta, x, y, z. If instead of these absolute angles, I use the Euler angles psi, theta, and phi, then the form of this matrix is going to be changed a little bit and describe them in terms of psi dot, what, theta dot, and, or no, actually, the q's are different things. So if I want to do that, then this matrix J is going to be a little bit different. That's what you see right now. We call it analytic Jacobian, and I assume, where is that? I have it here in slide number 8 of mine, and I'm going to talk about it, okay, in a few minutes. But I just want you to know that depending on how you represent the orientation of the end effector, what format you use, the form of your Jacobian will be different from what you see in here. And finding these functions is not always trivial. Plus, you have to make sure that these partial derivatives that you are taking here, you don't make any mistakes in them. Of course, you can avoid mistakes if you pay attention enough and if you use MATLAB Symbolic to take time derivatives for you, just to confirm your calculations. I don't mean you rely on MATLAB for doing your calculations for you. You have to do it yourself, but it's good to check and see whether you made a mistake or not. So you can probably avoid mistakes if you know basic calculus and you can use the software to confirm it. But finding these three functions is not always trivial, okay? And we'll talk about it again, as I said, in a few minutes. But I want to show you another approach to find the Jacobian matrix, and that is using the DH method. So if you remember, in the DH method, DH convention, it also gave us, when we used it for forward kinematics, it gave us this guy here, correct? If you remember, DH was also giving us this T. How did it do it? If you remember, we formed a bunch of A matrices, A1, A2, each one of them was the function of one of the joint variables, and multiplied all the way to AN. Again, each one of them was function of one variable, and each one of them came from one row in the DH table. We form each one of these A's and multiply them together. That gave me my T, and so that gave me my rotation matrix and O. Now that I have this general homogeneous transformation matrix between end effector and base, can I find the J matrix based on the result of this T? And the answer is yes. And actually, it is quite easy job to do that. And that's where the DH method can outperform the vector addition method that we had in terms of the Jacobian. So in terms of forward kinematics, if you remember, the Jacobian was not as easy as the vector addition method and doing pure algebra. But here, the DH method shows its power. I'll show you in a second. And you'll see finding the Jacobian matrix when you do the DH convention for forward kinematics is actually very easy. So now the question is, how do you do that? Let's talk about it. Okay, so let's look at this J matrix. And by the way, before we go and focus on the J matrix, what's the dimension? Let's talk very fast about the dimension of this J matrix. The matter of fact is this J matrix is not always a square matrix. It depends here that when we define this zeta, how we define it. In general, if we want to look at everything in 3D, then this zeta is always 6 by 1. Okay, it is what? 6 by 1. So it's not like if I don't like the 3D problems and I solve a 2D problem where some of these guys are simply 0, I can just resize J. Okay, so if we look at this problem we just solved, this 3D OF thing, where was it? See if I can find it here. The matter of fact is here I have eliminated 3 of the components of zeta. If those guys were there, then what happened to zeta? You would get what? You will get x dot, y dot, z dot and what? Omega x and omega y and omega z. Good. So the thing is, you don't have here any function for z, you don't have any function for theta x and theta y, so instead of them you have to write what? You have to write 0. So what you need is something like this. You have to expand this, bring this theta z down, and then say, well, z of the end effector in I is simply 0. The same thing for theta x and the same thing for theta y. And then what happens to the end effector? These 3 rows will not be a function of any of these theta 1 dot, theta 2 dot, theta 3 dot. So what happens to J? Your J will be basically something like this. 3 rows of 0 added. The last row will be 1, 1, 1. Okay, so if you really treat the end effector velocity vector 3D, then this matrix J in general is not square. The dimension of it in general is 6 by n, because zeta, the end effector velocities, are always 6 components, but your joints are not always 6. Sometimes your robot has what? Less than 6 joints, sometimes has exactly 6 joints, sometimes more. For example, the 2 or 3 DOF planar arm or Scara, they have less than 6 joints. Some of the robots we have seen, like the Stanford arm or the 6 DOF articulated robot, they have exactly 6 joints. And there are some robots that are redundant. They have more than 6 joints. So in those cases, your J matrix is in general a rectangular matrix, 6 by n, because your Q dot, your joint vector, is n. N here is the number of joints. So your J in general is what? 6 by n, where n is the number of joints. Okay, so that is your J matrix. Just keep in mind, it's not always a square matrix, unless your robot has 6 joints, of course. So now this is how we go about the Jacobian determination based on the DH method. this J matrix that we have, we consider it to be n columns. Remember, the dimension of this guy was what? It was 6 by n, which means there are n columns. Each one of the columns is what? A 6 by 1. So each one of these j's that you see here, each one of these j's is a 6 by 1 vector. Okay, so here you consider your J matrix to be made of n columns. And you call these columns what? J1 to Jn. Good? Now, when you multiply the J matrix by Q dot, by vector Q dot, which has all of the Q's in it, all of the Q dots in it, from Q1 dot to Qn dot. Correct? By the way, this has to be, let me fix this. Qn dot, and in general, it's not 6. So what I can do here is just get rid of some of these and just put a dot instead. No, just keep it. Also, see, there we go. So you have n joints, n of these columns. If you multiply, your end-effector velocity is going to be summation of ji times qi dot, correct? What's the meaning of this? It has a good physical meaning. It means what? Because these q dots are all single numbers, right? They are just a scalar. If you consider them like 2, 3, 5, 6, whatever, it means your zeta is what? Like 2 times J1 plus 3 times J2 plus 5 times J3 and so on all the way to, let's say, 10 times Jn. So what does it mean when you write something like that? When you say, for example, let's say you only have 4 joints. If you have 4 joints like Scara, your zeta is going to be what? Q1 dot. Let's just come up with some numbers for this vector. Let's say just 1, 2, 3, 4, just to make it simple. It is going to be 1 times J1 plus 2 times J2 plus 3 times J3 plus 4 times J4, for example. Right? What's the meaning of this? It means this vector zeta is a linear combination of the columns of the J matrix, correct? That's called a linear combination. So if I combine the columns of the J matrix in a linear fashion, the result of that is what? The end-effector velocity. Now, what are the weights of that linear combination? Those are what? The joint velocities. And another meaning is this. Which column of the J is closer to what? To the zeta, or it plays a bigger role, a bigger contribution to zeta. Which column of J has a bigger contribution to zeta? The one that has what? A corresponding bigger Qn dot, correct? The joint that rotates faster or moves linearly faster, it also, the J column for that joint plays what? A bigger role, a bigger contribution to zeta, okay? So you clearly see the physical meaning of columns of J and zeta. Good? So based on this relation here, you can simply say that if I take the partial derivative of the zeta with respect to any of these joint velocities, the result is what? The result is that column of the J matrix, correct? So partial derivative with respect to Q2 dot here, right? Take partial derivative here of zeta with respect to Q2 dot. What's the result? Of course, the coefficient of it, which is J2, correct? And again, here it clearly tells you the meaning. The change in zeta per change in what? The joint velocity. That's the meaning of each column in j, correct? In other words, for example, if I go back to my robot and look at some robot, let's look at some picture. This is my robot, okay? From the base, several members, going to some specific joint, going all the way to end effector. What's the meaning of column 2? Column 2 means what? Of the Jacobian. Means if I change my theta to dot from some number to another number, what's the effect of that on what? On the end effector velocity, correct? Yes? For example, if the relation is linear, means if I rotate joint 2 times faster, the end effector velocity, each component of it is going to be 2 times bigger, right? Or if this is nonlinear, then you can define it separately. But clearly see the change in end effector velocity per change in each joint velocity. That's the meaning of each column in the J matrix, right? So the meaning of it is very clear. Now that we know the meaning of these J's, can I easily calculate them from the DH convention? And the answer is yes. So what you do is only here, you divide your joints into 2 categories. You say either my joint is revolute, which is rotary, or my joint is what? Prismatic, which means they are only linearly going forward and backward, okay? So if that is the case, then how can I determine the contribution of each joint or each joint's velocity in the end effector velocity? How can I determine that? And it's not so hard. Why? Let's look at the prismatic because it's simpler. It says, hey, if the joint is prismatic and I move a prismatic joint, what is the contribution of that to the vector zeta? And if you remember, vector zeta had 2 parts. If you remember, the zeta had 2 parts. It has v of the end effector and it has what? Omega of the end effector, correct? This was the meaning of zeta. So basically, I want to know if I change the velocity of joint number I, how does it affect each one of these v and omega, and then the partial derivative of that, I call it what? Or the contribution of that, I call it ji, the ith column. So let's take a look here. If one of these joints is prismatic, when I move it, what's the effect of that velocity on the velocity of the end effector? What's the effect of that on angular velocity of the end effector, linear and angular? So let's forget about this complicated robot. Let's look at the simple robot. So let's say here I have a 2DOF planar arm. The first link is prismatic. So it, or let's make it 3 degrees of freedom to make it a little bit more complicated. So the first one is rotary, right? So let me show it in 3D. The first link is rotary, right? The second link is prismatic. And the third link is also rotary. Good. So if I move this prismatic joint up and down, how does it affect the velocity of the end effector, how does it affect the linear and angular velocity of the end effector? First, and when I say when I move the second joint, it means you do not change the angle or the values of any other joint. In other words, lock these other joints. In other words, make this Q1 dot equal to what? 0, and make Q3 dot also 0, right? That's the meaning of partial derivative. Remember, when you take partial derivative, what would you do for one variable? You assume all other variables are constant. Remember what we did here when we did this method, correct? When we take partial of f1 with respect to theta 1, I treat theta 2 and 3 as what? Constant. The same thing here. When I'm taking partial of zeta with respect to q2 dot, I'm assuming that my theta 1 dot and theta 3 dot, or q1 dot and q3 dot, are what? 0. I consider them as 0, right? Or their angles, I consider their angles as constants. Their angles are not changing. Okay, so if you lock those, in other words, correct? Make Q3 constant. And Q1 constant. Just move this prismatic up and down. What's the effect of that on the angular velocity of the end effector? And you would say nothing. If here I like these two rotary joints, just go up and down, is the end effector going to rotate? Do I gain any angular velocity by just going up and down? Of course not. So the contribution of that omega with respect to this Q2 is simply what? 0. There is no contribution. Now, if this omega has 3 components, which it does, then this 0 is going to be a 0 that has 3 components, because it doesn't give you omega x, it doesn't give you omega y, it doesn't give you omega z, so it is going to be a vector of 3 zeros, right? So a linear motion of one joint will never create angular velocity for the end effector. Therefore, you can see here I have what? I have a vector 0. So this 0 that you see here is a vector. It's 3 by 1. Okay? The same thing for everything else. Everything else here is a vector. It's a 3 by 1 vector. Good, so that is clear. Now, what about the linear velocity of the end effector? What's the contribution of Q2 dot on V? What about that? Is that going to affect V? Of course. If I like everything up, when this guy goes up and down, this end effector also goes what? Up and down with the same value as Q2 dot, correct? So this Q2 dot will be added to the current velocity of the end effector. Or if there is no other component, V is simply going to be the same as Q2 dot, because now your whole robot is like a rigid body, one single rigid body. Once you move one point, every other point will move the same way. So what is going to be the partial derivative of V here with respect to Q dot? Well, you might be tempted to say 1, because V is going to be the same as Q dot. You might tempted to say, but yeah, it's 1 or maybe 3 ones or something like that. The answer is not exactly. Why? Why is that? Because along which direction this Q2 dot is happening? What's the direction of this Q2 dot? Along which axis it is happening? Well, this is joint number 2. Joint number 2, what's the actuation axis of joint number 2, if you remember from the DH method? Right? If you remember from DH method, the actuation axis for joint number I is axis what? Zi minus 1. So the direction for this vector is what? Vector Zi minus 1, which is in this case is Z1. So this Q dot is happening along what? Z1. So V, the magnitude of it is Q dot, right? But the direction of it is what? Z1. So I should write V as what? Q2 dot times what? Z1. Any vector can be written as its magnitude times its unit vector. Now when I take partial of V with respect to what? Q2 dot, the answer is what? Vector Z1, the actuation axis of joint number 2 or Z1, right? Correct? And of course, Z1 written in what? Written in the inertial frame, correct? So vector Z1 written in the inertial frame because this is V of the end effector in what? In the inertial frame. And this is omega of the end effector in the inertial frame. So that is now equal to J2. So J2 is going to be Z1, or Ji is Zi minus 1, which you can see here. Right? So if joint is prismatic, the contribution of the motion of that joint toward linear velocity of the end effector is Zi minus 1. Toward angular motion of the end effector, there is no contribution, so it's 0. So here, and clearly, as I said, each one of these is a 3×1 vector. So when you stack them on the top of each other, the result is going to be what? A 6×1 vector, which, as we said, that's the dimension for one of the columns. So for a prismatic joint, getting Ji just requires you to find Zi minus 1. And I'll tell you how to find it. It's very easy. What about when the joint is revolute? If joint is revolute, then what? Then again, this revolute joint will contribute to what? To the end effector linear velocity and angular velocity. How? Let's take a look. So what I do here is I rotate what? One of these rotary joints and lock the other ones. So let's say here I rotate joint number 1. And I want to look at the effect of the RPM of joint 1 on the end effector velocity. So what I will do here is I'm going to rotate this guy with theta 1 dot. This Q2 dot, I set it equal to 0, which means Q2 is constant. So this prismatic joint here is not going to go up and down. It's going to stay in the same position. That joint is not going to rotate. It's going to stay at the same angle. This is the end effector linear velocity. And this is the end effector angular velocity. So what's the effect of this theta 1 dot on each one of those if I lock every other joint? Well, first, what's the effect of theta 1 dot on omega dot? If I lock everything else, then the whole robot will rotate like a rigid body about the axis of what? The axis that this theta 1 dot is happening, and it is going to be what? A pure rotation about the fixed axis. That's all it does, correct? It is a pure rotation about the fixed axis. So if I say, okay, what is omega? Well, you say omega is the same as theta 1 dot, except theta 1 dot is just the magnitude. It also needs a direction. And I ask you, what's this axis? What's the axis for joint 1? For theta 1 dot, what's the axis for it, for joint 1? What is this axis? And you say the actuation axis for joint 1, we call it what? Zi minus 1, which in this case is called what? Z0. So I can write it as theta 1 dot times what? Z0. Of course, Z0 in I. So now if I ask you, what is the partial derivative of that omega with respect to theta 1 dot, what would you say? Take a partial derivative. Clearly the answer is what? Z0. in I. Done. Correct? So the angular contribution of theta 1 dot is the axis of actuation for it. So if it's theta I, it's going to be zi minus 1, which again you can see here. The contribution of a revolute joint on the omega. It's zi minus 1. Again, this guy is a 3 by 1. Right? Now, the kind of, you can say, most complicated part is when the joint is revolute and you want to see the effect of that on linear velocity of the end effector. What is that one? So here, this time I'm going to what? Rotate this joint only, nothing else, and see what kind of velocity the end effector will get due to this pure rotation theta 1 dot. Well, what is it? What do you think? To do that, to show that a little bit clearly, maybe we can focus on this other picture. This can tell me a little bit better. So take a look here. Instead of theta 1 dot, here I use a middle joint. So here is my base. This theta I is a middle joint, so it's not the joint right at the base, and it's not the last joint. It's somewhere in the middle of the robot. I want to see the effect of theta I dot on the velocity of the end effector. What is that? If I, like the rest of the robot, only rotate that joint, what kind of velocity does this end effector, linear velocity, does it get? And the answer is, if you remember from rigid body dynamics, if this is a point here, and this is the center of rotation, correct? And if the point of interest is here, yes, if this vector is r, and it is rotating with angular velocity omega, in general, v here, the velocity, if you remember from rigid bodies, it was what? It was omega cross r, correct? Where omega was the angular velocity and r was the distance from the point of interest to the center of rotation. If I cross these two, that was the v due to rotation, correct? Now we're going to use the exact same thing here, with the difference that here my end effector is not rotating about the base, it is rotating about what? Joint I minus joint I, I'm sorry, joint I. That's joint I. This is joint I. So my end effector is rotating about joint I. That is the center of rotation. Good? So if I have this vector r that you can see, this r, this guy from here to here, if I have this r and that omega, omega cross r will give me the velocity. The question is, what is this r? This r is from from joint I to the end effector, which I do not have directly in the DH method, but what I have in DH method is the position vector of joint I in the base frame and the position of the end effector in the base frame. In other words, DH method will give me both of these vectors in red, and I'll show you why and how. In DH, I can easily get both of these vectors in red. Now, how can I get this vector in blue? Well, it's clear. I will subtract this vector from this one. This is the origin of frame I in base. This is the origin of the end effector in base. If I subtract, that's R, and that's exactly what you see here. This guy. This is that R vector. Okay, that you're seeing over there. Now, why is it cross multiplied by zi minus 1? Well, because this omega that you have, it has what in it? It has theta I dot That's the magnitude of the rotation. And the direction for it is what? Remember, actuation axis, the unit vector, the actuation axis for joint I is what? Zi minus 1. So this is the omega vector, and that R, as you saw, is the origin of the end effector in base minus the origin of frame I in base. Okay, this is going to be that resulting V of the end effector in base. Or here we have to say n in 0. Now question, what is the partial derivative of this Vn0 with respect to theta I dot? Well, clearly it's the rest of it, which is Zi minus 1 cross On minus what? OI, which you can see here. And again, this R is a 3 by 1 vector, Z is a 3 by 1 vector, so when you cross product it, it's also a 3 by 1 vector. And again, 3 by 1, 3 by 1, you stack it, you're going to get a 6 by 1. So if you want, there is proof behind it also, but the proof is exactly what I just said here verbally. It's nothing more than that, okay? So I can write everything I said in a nice, in a more neatly format, but that's all it is, okay? I try to make it very simple for you. So if the joint is revolute, I know how to calculate the ith column of the Jacobian. If it's prismatic, I know how to calculate the column of the Jacobian for that joint. And once I have all these joints, I calculate the column for them, I put them side by side, and that will give me what? My J matrix. Now, the question is, how do I get these entities? How do I get Zi minus 1 that I need? How do I get On? How do I get OI minus 1? And they're all with respect to frame 0 here, or I. How do I get these? What does these have to do with the DH method? Well, let's go and look. So if you remember, we just were talking about it. This T of n with respect to 0 gives you rotation matrix and origin of end effector in frame 0, but that's not the only T you can get from DH method. You can also get T of any other joint or any other frame in frame 0, okay? It's not just the end effector. For example, I can get T of frame I minus 1 also in the base. And if you remember, it will be the rotation matrix of this frame in the base as well as the origin of this frame in the base. And a bunch of zeros and a 1. Now, the question is, what does these Z's that are quite common in this formula, what do they have to do? And also that O, they are all I minus 1, what do they have to do with this T matrix? Okay, first of all, how did we get this T matrix? If you remember, this was A1 of Q1 times A2 of Q2 all the way to AI minus 1 of QI minus 1. While this one was from the beginning all the way to the end. Correct? So depending on where we stop multiplying them, we will get the T for that frame with respect to the base, okay? So, and I have all of these A's from the DH method and DH table, so I can multiply as many as I want. Now the question is, what is Z, what is O? Well, first of all, you clearly see here the fourth column of this matrix is clearly what? OI minus 1, which is exactly this. So all I need is to look into the fourth column of Ti minus 1 and look at the first three numbers, not just this one. Forget about that one. That one is always there. The first three numbers of that matrix. So if this T matrix in general, if this guy here, this T matrix, is like what? It is like T11, T12, T13, T14. Then we go T21 all the way to T24. And then we go T31 all the way to T34. And then we go with 0 and 1. The question is, which part is O that I need? It's these three numbers in the last column. Entries T14, T24, and T34. These guys are OI minus 1 that I need in that formula, if it's a Revolute joint. What about Zi minus 1? Well, if you remember, these 9 numbers, or these 3 columns, are this rotation matrix. And what was the definition of the rotation matrix? If you remember the definition of the rotation matrix, what's the meaning of this? It is x of frame I minus 1 dot x of 0, and then the same x dot y of 0, and what? Z of 0, correct? That's the definition. That's the first column. And then you get what? You get 2 more columns like that, where one of them is for y, one of them is for z, correct? So let's see here. There's another one, and here there's another one. Good. So let me just modify it very fast. So these guys are y, and these guys are z. And now if I ask you, what is this third column giving you? This is giving you the vector zi minus 1 as written along the axis of frame 0. So I can write this as what? Zi minus 1 written in 0 as a vector. And guess what? That's exactly what you want here. So what? And this is the third column of R, which is this guy here. This one. This one is your Zi minus 1, which you were looking for. So if I have T of I minus 1, the third column of that and the fourth column of that are going to give me what? Zi minus 1 and OI minus 1, just like that. And what is that ON? Well, that's a similar thing, but instead of, it's the last column, that's ON, but instead of for frame I minus 1, it is for frame what? N, for the last one. So it's exactly this guy here. The fourth column, the first 3 numbers in the fourth column of T0, N, that is exactly what comes here. And done. So you see, once you have the T matrices in the DH method, all you need is to look into the third and the fourth column of the T matrix. That will give you everything you need here to calculate the columns of the J matrix, and then put them side by side, and it's over. Okay, and it's very systematic approach. You don't need to find these explicit functions and then take partial derivative of them, because as I said, the XYZ are not too bad, but these guys are not always trivial. Okay, but here it doesn't care as long as you form your T matrices. So now, to make this a little bit cleaner for you and more obvious, Let's go and look at a couple of examples here so we can digest this material a lot better. So we want to go and look at the planar arm example again, 2DOF, for which we have the Jacobian from our previous examples, correct? And see what we get. Well, if you remember from the DH method and the 2 degree of freedom planar arm, we had two A matrices. We had A1 and A2. That's all we had because it has only 2 degrees of freedom. And I don't know if you remember these A's and not. So they are 4 by 4 matrices. Let me make them a little bit bigger. If we go back and look at our lectures, this is 0, 0, 0, 1. This was a rotation Z with angle theta, so it should be like 0, 0, 1, 0, 0. This is C1, negative S1, S1, and C1. And this is the location of origin of frame 1 in frame 0, which was A1, C1, A1, S1, and 0. This is the A1 that we got from the DH method. And getting these A's is not hard because the A's, if you remember, it has a general formula based on the 3 parameters, alpha I, di, theta I, and ai, correct? You remember? Each row in that table has all of these 4 numbers. And then A in general was based on these 4 parameters, the components of it. The last row is always 0, 0, 0, 1. So it's only these 12 components that are formulated based on these guys. And if you remember, in general, AI was a rotation of z and theta I times a translation of z and di times a translation x and ai. Hopefully this one will go away so I can continue. Followed by a rotation of x and alpha I. So it was, each component in it was a function of one or a few of these variables. And if we read the 4 numbers from each row and plugged in, it will give us one of these A's, correct? And when you multiply several of these A's, you will get an appropriate T. So just go back and look at the 2 lectures we had on the forward kinematics using the DH convention, okay? So plug and play, okay? It's not really hard to digest and understand. So that was A1, and then again A2, if you remember, is similar, correct? Except 1 becomes 2. And this is 2 in 1, so you will get A2, C2, A2, S2. And then T1 is simply A1, so T1 and A1 are the same. That's it. And T2 was A1 times A2, so you have to multiply these guys together. And if you go back and look at the DH method again, I guess it was C12 negative S12, where 1, 2 means some of them. S12, C12, 0, 0, 1, 0, 0, 0, 0, 0, 1, and then what? This one was A1, C1 plus A2C12. This one was A1S1 plus A2S12, and this was 0. Okay, so these were the only two t's that I need because for this robot, n was 2. Okay, that's all it is. So clearly my j, in general, if I consider the end effector to have 6 linear velocities, this is going to be a what? A 6 by 2 in general. So the question is, what is this? Well, clearly here we consider it to be column 1 and column 2, where each column is clearly a 6 by 1. Now, how do I get these columns? Well, we go and use the formulas that we have here. Now, both of the joints for this robot are Revolute. So for both of them, I have to use this formula, the top one. So clearly, get rid of the Scara. Clearly, your J1, the first column, is what? The top 3 components of it are Zi minus 1, On minus Oi minus 1. Now, I here is 1, so Zi minus 1 means Z naught. Cross On, which is O2 here, minus what? This should be O2, O0, both of them in 0. Correct? And this is, of course, Z of 0 in 0. Everything here is with respect to 0. And then here is simply Z of 0 in 0. Or if you want, you can get rid of all of these extra zeros, because we know the reference here for everything is the base. So it is going to be like that, based on what we have. Okay, what is it now? What is Z0? Z0, what is Z of 0 in 0? What would you say? Okay, because if you remember, if we want to find Zi minus 1 and Oi minus 1, I have to go and look into Ti minus 1. And since I minus 1 here is 0, means I have to look into T0. But there is no T0 here. We only have T1 and T2. T0 is anything in itself. It's the base frame with respect to itself, which clearly has what? It has no, if you ever want T00, you don't have to, but if you want T00, let me get rid of this. If you want T00, it's the first frame written in itself. Well, what do you think the answer is? That's right. The rotation matrix is identity because there is no rotation, and the origin of 0 in 0 is all zeros. So T0, if you ever want it, it is the identity matrix for rotation and a bunch of zeros for the origin. And the last row is always constant. So this is O of 0 in 0, and this is what? Z of 0, which of course it's the z-axis 0, 0, 1. So Z0 is simply what? 0, 0, 1, no big deal. What is O0? Of course, that's the origin of the base. That's O0 here. That's not a big deal. And what is O2 now? Well, O2 comes from T2, and T2 is this guy, so this is O2. So just subtract O0 from O2, which is going to be the same as O2, and cross-multiplied with this. So basically cross-multiply this by that. Z0 cross O2. Right? So it is going to be this vector cross that vector. And this is just going to be 0, 0, 1. And if you calculate it, what's going to happen? The bottom part is clear. What's going to be the top part? Okay, if you do it, it's only k, right? K cross I is negative, k cross I is j, k cross j is negative I, k cross k is 0, and there is no k. So it's going to be negative of this guy as the first component, positive of the second one for the second component, and then there is no z. So this is the top portion of it, and then the bottom portion of it is clearly 0, 0, and 1. So this is your first column of the Jacobian. What's the second column? Similar. Second column is, instead of zeros, you have to plug in 1, because the index here, here, and here is always 1 less than that. So it's going to be Z1 cross O2 minus O1 and Z1. And what is that? Where do I get those? Well, O2, I already have it. I know it. What is O1? What is Z1? For that, I need to go to T1. This last column here is O1. The column before that is what? Z1. Or Z1, you want to write it as a vector. That's okay. It's a unit vector, so it's better to use hat. That's it. So let's plug in. Again, this is just 0, 0, 1. And this is 0, 0, 1 cross. Now you have to subtract those two. When you subtract these two, the first element in O2 would go away. You see, this O1 and O2, when you subtract O2 minus O1, this first element would be cancelled. So all you will get is a 2C12, a 2S12, and 0. And when you carry out this one, you will get something similar again. It's negative a 2S12, negative or positive a 2C12, and 0 for the first three, and then for the next three again 0, 0, 1. And now put them side by side. J is J1 and J2. So all you need is to just bring these guys and put them side by side. Done. This is my J, which is a 6 by 2 clearly. Is that the same thing that we got when we did those partial derivatives? Absolutely. Let's go back and look at it. Let's see if I have it somewhere. Here. Similar to this. Don't know if I have it somewhere, but hopefully I do. Yeah, you see? These are, no. Seems like I cleaned it, but that's okay. You clearly see here when I ignore theta x, theta y, and everything else, these guys are exactly here. Because this robot does not have a theta x. In this case, your theta x is simply 0. It has no role, no contribution from theta 1 dot or theta 2 dot. So both of these are 0. When theta y in general is 0, or theta y dot is 0, you can say both of them, it means these guys are 0. And since the z of the end effector is 0, well, I guess the order has to change. The top one is z. The z is 0. The first one is 0 because theta x is 0. The second one is 0 because theta y is 0. The third ones are 0. And what about theta z? Well, in this case, clearly theta z is theta 1 plus theta 2. So if you take partial derivative, you will get this. So you see the derivative of omega z with respect to theta 1 dot is 1. With respect to theta 2 dot is also what? 1. So this is the 2 degree of freedom planar arm, the Jacobian of it, if you consider everything, okay? In general, if you consider that zeta vector to be 6 by 2, as it is in real life, then Jacobian is going to be 6 by 2, and this is that Jacobian. Okay, so hopefully getting this is not as bad. Now, if I want to show you another example of this, we can look at, for example, a Scara. So for a Scara, we had the DH table and everything, and for that we can get the T matrices. Now let me show you the T matrices for it. So the T matrices for a Scara are these guys that we have calculated, or I have calculated. That was the robot, the frames, frame 0 all the way to frame 4. The specs for it, it had theta 1, theta 2, d3, and theta 4. There is also this constant d4 here, the offset. These are the T matrices from T1 to T4, and now I can use the third and fourth column of these matrices to calculate J1 to J4, the 4 columns of the Jacobian matrix. So if I want J1, well, the first joint is rotary, so it is going to be Z0 cross O4 minus O0. And then Z0. Okay, where do I get Z0 and O0? All of it from T0. Again, there is no T0. And you know, whenever you're down to this very first one, your Z is always the Z that we always have in our XYZ coordinate, 0, 0, 1. And your O0 is simply all zeros. Okay, so this first one is no big deal. O4 is this guy here. So if I plug that in, do a cross product, since this O0 has all zeros, you basically exactly get that O4 cross multiplied by this. Always, you know, K cross I is J, so that component comes to the second column positive, the J goes to negative I, and then K cross K is 0 regardless, okay? So you're not going to get anything out of K cross K. So you will get, as I said, negative A1 S1, negative A2 S12, A1 C1 plus A2 C12, and 0, that is for the top part, and the bottom part is simply 0, 0, 1. So that is the first column of your Jacobian. Move to the second column. Second column, again, second joint is rotary, so it is going to be Z1 this time, cross O4 minus O1. Then here is going to be Z1. Where do I get Z1 and O1? Because O4 is the same thing. I go to T1 this time. Look at T1. This is your Z number 1 and O number 1. And this is your Z number 1. Now pay attention that these calculations might look a little bit too much and intimidating sometimes, but for a computer, if you program them very nicely, they are nothing. Okay? For a computer that can carry out all these matrix products and read your DH table, so all you need to really give to your code is the DH table. Then it plugs in, finds all of the A's, and it keeps multiplying the A's to get all of the T's, and then reads the columns 3 and 4 of the T's, plug them here, and you just need to tell it which joint is what, whether it's rotary or prismatic. So it uses the appropriate formula, calculate the columns, put them next to each other. So for a computer, if you program it well, since they are very good, like MATLAB especially, for multiplying matrices and reading a column of a matrix or anything like that, writing this and allowing it to calculate the complicated Jacobian matrix for robots with high degrees of freedom, with this way, it is going to be quite easier than actually going and calculating those functions for the angle that are not always trivial. But anyways, the calculation of Jacobian is not something that is super easy. Okay, you have to work a little bit on that. So Z1 is, but once you do it one time, you can use it forever. So that's your Z1 that's given. Then here you have to subtract 04 minus 01. So this A1C1 and A1S1 gonna go away. And your Z is still 001. So again, you will get something similar except for the first component gone because you subtracted 01 from that, and 01 has both of those. So you will get A2, S12, A2, C12, and 0, and again 001. That's the second column of the Jacobian. Then we go to 3, column 3. There are 4 columns in general because there are 4 variables. Now for 3, the third joint is prismatic, right? The third joint is prismatic, so we have to use the prismatic formula, which, if you remember, it's even simpler. It says simply Zi minus 1 and a bunch of zeros. So prismatics are really easy. So all you need here is Z number 2 and a vector of 3 zeros. That's all it is. It's very easy. And where do I get Z2? Well, all I need is to go to T number 2. This guy here. That is Z2. Just 0, 0, negative 1. So here we go. It's going to be 0, 0, negative 1 for the top one, and the bottom one is all zeros. Done. You see, this column is not even a function of any variable. The first 2 columns are functions of theta 1 and 2, but this one is clearly not. It's just a constant column. And then J4, again, that's rotary. So you need Z3 cross 04 minus 03. And Z3. And again, you go and look. Z3 and O3, you go to T3, and this is your O3, and this guy is your Z3. Okay, so Z3 is clear. When you subtract O4 and O3 from each other, all you will get is, so the first 2 elements are 0. This is going to be just a negative D4 remaining, correct? Yes. So you have to cross multiply 0, 0, and negative 1 by really 0, 0, and negative D4, correct? As far as I can tell. Because that's O3, that's O4, you subtract. That is what you get, and these are both k vectors. K cross k is not going to be anything. It's going to be pure 0. I just wanted to make sure when I subtract 04 from 00, and cross multiply that k by those. Yes, k only that does have cross with I and j. That's good. Here z1 was similar, so no worries. Here z2, this one was so clear. Here z3, yes, that's this one, that's the subtraction. Again, this is going to be pure zeros, so this is going to be all zeros, and z3 was just 2 zeros and a -1. So you see the fourth column is also a constant column. And so once you put all of this together, your Jacobian is going to be see if I can get this portion. Good. And the rest of it is not that bad. 0, 0, -1, 3 zeros, and then 0, 0, 0, 0, 0, -1. So this is your Jacobian. Done. Okay, so that's the Jacobian of the Scara, and you can get Jacobian of anything else. Okay, and if you look, the first two columns of it are exactly like the 2DOF planar arm, because a Scara is something like that, really. Okay, the last thing I want to talk about, although the video is getting long, but I think it's relevant that we talk about it right here, is analytic Jacobian versus geometric Jacobian. And I told you the difference is really all depends on how you define this omega. Okay, this omega is time derivative of what angles. When we define this geometric Jacobian, this J that we calculated so far, this omega, or the components of this omega, were what? The time derivatives of theta x, theta y, and theta z. Where they were the absolute angles of the end-effector frame in the base frame. Absolute angles, extrinsic rotations. But most of the time, these angles are not how we measure the orientation of the end-effector. And so when we take a derivative of them, then the omega they give us is also not this omega, it's a little bit different, right? The question is, if we change this omega to be, let's say, the omega coming from Euler angles, then how does my Jacobian would change? And here, let's take a look. So here I assume that I have three Euler angles, phi, theta, and psi. Here the order is reversed. Instead of psi, theta, phi, theta, psi, but it does not really matter. It's just notation. So here the orientation of the end-effector frame with respect to the base is shown with three Euler angles, phi, theta, and psi. If you remember, in one of our previous videos, I showed you, if I know the Euler angles, how can I get what? The angular velocity of the end-effector in base, or in end-effector in inertial, if I know my Euler angles and their time derivatives, phi dot, theta dot, and psi dot. How can I find my omega of the end-effector in inertial frame? Please go and watch my video on Euler angles. You'll see how this guy is calculated. I calculated it in two different ways. One was using rotation matrices and projecting everything back to the iframe. One was using geometric projections and showing you with geometry, really. But this is the omega of end-effector in base based on those three Euler angles. So you see, it's not as simple as the time derivative of three angles. Not only the time derivative of the angles theta dot phi dot psi dot are involved, there are sine and cosine of the angles are also involved, because these guys are intrinsic angles. They are with respect to the current axis. Not all of them are absolute angles. Okay, so for that reason, your omega is different. Now, this is what I do. If here I define my end-effector velocity to be what? The time derivative of the position of the end-effector in base. So if d of e with respect to I here is the position of the end-effector origin with respect to the base, if I take time derivative of that, this is clearly what? That velocity. Okay, which is the same for both of them, for both representations, whether you use absolute angles or use what? Euler angles. V is not going to change because V is only depending on x, y, and z. It has nothing to do with angles. But here, zeta was the vector omega, which was based on absolute angles. Here, my angular velocity is defined using alpha dot, where alpha was the vector of the three angles. Okay, and when I say alpha dot means what? It means phi dot, theta dot, and psi dot. The angular velocities of the Euler angles. The Euler angular velocities, basically. Then I cannot say this guy is the same as this one. These two are two different things, right? At least the bottom portion of them are different. The top portion of them are the same. The bottom portion are different. These are the derivative of the absolute angles. These are the derivative of what? The relative angles. But can I relate them to each other? The answer is yes. So how can I relate them? So this is what I do. This zeta that we defined and we calculated so far, if you remember, it was equal to J times Q dot, correct? And this J that we so far been calculating, we call it geometric Jacobian. I can also define a similar Jacobian for this new for this new end-effector velocity vector, this x dot, where clearly here x means what? When we say cap x, this cap x here is what? The x of the end-effector in I, the y of the end-effector in I. This x and this x are different. That's a scalar. This is the whole vector. The z of the end-effector in I. And then what? The three Euler angles, which are phi, theta, and psi. So this is the position of the end-effector. Time derivative of that is going to be the velocities of the end-effector. For this one, since it's different from zeta, if I want to write it as a matrix times the joint velocities q dots, this matrix which relates q dot to this one I call analytic Jacobian. And now the question is, are these two geometric and analytic, which are using different angles and of course different angular velocities? By different angular velocities, I mean theta dot phi dot psi dot versus theta x dot, theta y dot, and theta z dot. Can I relate them? The answer is yes. How? So take a look here. this matrix, this vector that I found, the Euler angular velocities, combined with sine and cosine to give you the omega of end-effector in base, I can write it as a matrix product. I can write it as a matrix of theta, phi, and psi. And since theta, phi, and psi, we call it alpha, I can call it this matrix what? B of alpha. Or you can say this is a matrix B of what? As I said, phi and theta and psi, because you see all of those parameters are, actually it is only theta and psi. There is no phi in this one. So it is actually like this. It is theta and psi. Okay? But if you consider that this is also a function of phi, but the functionality of phi is 0, so there is nothing in it, then you can call this whole thing to be your alpha. So you say this is my matrix B of alpha times these alpha dot times this phi dot, theta dot, and psi dot, which I call what? Alpha dot. So you see here, again, if the angles were absolute, the omega of end-effector in base would simply be what? Simply 3 components, theta x dot, theta y dot, theta z dot, done. But now that they are Euler angles, it's not simply equal to these 3. It's equal to a matrix times those 3. We call it B. So it's B alpha times alpha dot. Now, if you replace that here, what happens? If you replace it, so this is your zeta. Let's start with zeta. Zeta is equal to J, Q, and Q dots. And it's also equal to V and omega. V was D dot. And omega, instead of writing it as this, I write it as this top relation. Omega is B alpha times alpha dot. And then I rewrite this again into a matrix format like that. Why? Because I want to pull this out. And remember, this one was what? This is that x, big X dot. So I'm trying to relate zeta to x dot. And you see the relation is done via this matrix, where a portion of it is B of alpha. And since this x dot was itself analytic Jacobian times q dot, now these guys are equal. And if you get rid of the q dot, you see the relation between analytic Jacobian and what? The geometric Jacobian. So you need to multiply geometric Jacobian by this, which is I0, 0, and B alpha inverse to get what? Analytic. And if you want to know about the shape of this matrix, what's the size of that? Well, it depends, of course, on the number of joints, right? But let's say here you have 6 joints. Okay, so both of these guys are 6 by 6. Right? Or if you have arbitrary joints, just n, then both of them are what? What is the dimension for each one? Remember, they are both 6 by n. Correct? So what's the dimension of this matrix? What would you multiply by 6 by n to get another 6 by n? Of course, 6 by 6. So this matrix is always 6 by 6. So when it says 0, it's not just one number 0, it's a 3 by 3 0 vector matrix. This is also a 3 by 3 0 matrix. This is I 3 by 3. And this B alpha inverse is also 3 by 3. So if you look at it, it looks like this. 1 0 0 0 1 0 0 0 1, that's your I. Then you have 2 0 matrices, all 0. So it looks like this. and then you have inverse of this matrix, inverse of this 3 by 3. So you have to invert that matrix, and if you want, I can do that for you here, just as the last practice. So what I need is psi and theta. I call it T and P if you don't mind. And my matrix B is going to be what? It is going to be cosine sine theta, cosine psi theta, sine psi times sine theta, followed by negative sine psi and 0. The next one is sine psi sine theta, sine psi sine theta, cosine of psi and 0. Cosine theta 0, 1. And then all I need is to invert B. Correct? There we go. Here. Ooh. I think that's, let me see if we can simplify the answer. Yes, it did. Good job. So it is going to be cosine psi divided by sine theta. So this part I have to make a little bit bigger. See if I can move it a little bit. We'll see if we can expand this. Oh, didn't get one of the zeros. Okay, let's see if we can squeeze this in. So cosine psi divided by sine theta. Cosine psi divided by sine theta is this element. Then you have sine psi divided by sine theta and 0. And then you have what? Negative sine psi cosine psi 0. And finally, negative cosine psi cosine t over sine t. Cosine psi cosine t sine t. Negative cosine psi cosine t over sine t. Theta actually, not t. And negative cosine t over sine t, sine psi, and 1. So it's the same as this, except it is sine of psi. Yes. So this is going to be that matrix that you have to multiply by whatever Jacobian that we had from the previous cases. Let's say, for example, with the Scara, right? Or with the 60 OF. Of course, for the Scara, you only have one angle. You have no problem. This is really the case and the useful thing when you have 3 rotary angles at the end. So like you have a spherical wrist. Okay, so your robot is dexterous, so you can determine the orientation of it with 3 angles. That's where this guy comes very handy, because instead of absolute angles, you most of the time use Euler angles, and then You have to multiply this by whatever Jacobian that we calculated, so you get what? The analytic Jacobian. And what's the good thing about this analytic Jacobian? If you multiply this analytic Jacobian by x dot, y dot, z dot, and then what? Phi dot, theta dot, and psi dot, that will give you the what? It will give you the end-effector velocity like this. Or if you wanted zeta, zeta is what? J times q dot, correct? And the problem is with this q dot. If you have q dot and j here, you clearly see, if you look at j is this matrix times j inverse. So j is this times j analytic. So I 3 by 3, 0, 3 by 3, 0, 3 by 3, and b of alpha 3 by 3. So if you have Jacobian analytic, then you multiply this matrix, but that guy will come in to play here, correct? And you get this one. Let me just write this one fast too, so our notes are good and complete. And it was basically, let's see if I can do, no, I can't. Cosine psi sine theta. Negative sine psi 0. Sine psi sine theta. Cosine psi 0. And then we have cosine theta 0 and 1. So if you have analytic Jacobian, you multiply by this matrix, that will give you geometric Jacobian, and then you can multiply by q dot to give you what? Vector zeta. So depend on what your sensors are giving you, whether your sensors are giving you the Euler angular velocities or they are giving you the absolute angular velocities, you can basically use them along with Jacobian geometric or Jacobian analytic to get the end effector velocities, okay? So it all depends on what your sensors are returning to you. Okay, so hopefully this long lecture was useful to you. There are several other topics that we have to cover, and we will, but this video is already too long, so let's see you in the next lecture. Thank you.